Welcome to this lecture course on Big Data and Artificial Intelligence, AI in Material Science. The idea of this course arose about 1 year ago from discussions with the students of the Max Planck Graduate Center for Quantum Materials. Therefore, these students are a target audience of the lectures and exercises, but this group is significantly complemented by students from the Nomad University, from the Fritz Haber Institute, and from several other places. My name is Matthias Scheffler, and I am one of the organizers of this course. The other organizers are Claudia Draxler and Santiago Rigamonti, both from the Humboldt University zu Berlin, and Luca Giringhelli, who is, like me, from the Fritz Haber Institute of the Max Planck Society. On this slide you see two logos. At the top left, Nomad, which stands for Novel Materials Discovery, and you will learn more about this later. And at the top right we have the logo of the Max Planck Society, the Minerva, the goddess of wisdom and sciences. Let me start with some more general remarks, and then I will get more and more special. What do we want to achieve in this course, and how do we want to achieve it? Now, this course will cover classical and recent AI methods for material science and engineering, and with classical I mean fitting techniques or regression techniques, which still are at the heart of machine learning, but they are now viewed very much in terms of a systematic utilization and implementation of statistics. There are many AI methods, but for a certain problem, each of them has advantages or disadvantages. Sometimes even older methods, for example regression trees, may work as good or even better than more recent methods. There is no method that one can use blindly, and there is no method that is guaranteed to work for everything. In fact, material science is quite special in terms of the quality of data and in terms of the complexity and intricacy of processes that determine materials' properties and functions. Thus, several of the existing methods have been modified or advanced, and new methods have been developed for materials data during the last years, and these developments and inventions are ongoing. We are experiencing a deluge of data and information, but the increase in understanding and knowledge is somewhat slow. Typically, we still like to achieve that the modeling by AI is interpretable. We want to understand why a model works and why it fails. By the way, we call the result of a machine learning fit of data a model. That is, the ML algorithm together with its parameters is called model. Not all machine learned models are interpretable. In fact, probably very few are. This is something to think about. The word learning in machine learning, but also in normal life, has not much, if anything, to do with understanding. Interpretability of a model implies a big part of understanding, and the optimum even would be causality. With causality we mean that we can explain a feature X causing a result Y, and this is because, for example, if the feature is electric voltage put at a thin wire, that will heat up the wire, maybe making it even glow. So voltage causes heating up, and this is because electrons travel through the wire and scatter at lattice vibrations. Neither interpretability nor causality are necessary for machine learning. I would even argue in this course that the power of AI is utilized often best when the relationship between input parameter x or feature x and the measured quantity, the property or function of the material y, is so complex and so intricate that we should be happy to find a model that brings us from x to y. And we should not ask for understanding this algorithm and parameters. An example is that x describes the material and the temperature, and y is the performance of a catalyst for a certain chemical reaction. The relation between the material and the catalytic performance is so complicated that you cannot describe it easily. There are so many processes which support or hinder the effect. It's actually extremely intricate to describe that, if possible at all. And in fact, this will be demonstrated in the very last lecture of this course. Thus, describing relationships or correlations is the goal. Asking in addition for interpretability and understanding may be just an unnecessary request. I'm not sure if I would like to agree with what I have said, but this is something to think about. And I will come back to causality a little bit later in my talk. Let me now briefly go through the lecture to explain what we have planned. So at the moment we are at my lecture, which gives you a general introduction, more or less using transparencies which I had created during the last 5 years. But then in the second part I will in fact enter statistical learning and giving you some key important definitions. We then continue with a lot of discussion, which is crucial for machine learning and artificial intelligence, on data handling, repositories and archives. We will discuss then by Luca Guerin-Kelly artificial intelligence. Luca will give actually 2 talks on artificial intelligence. There will be another talk by Luigi Sbaio, by Daniel Speckart, Santiago Rigamonti, and Angelo Ziletti will give 2 talks on neural networks. I will talk again, Santiago will talk again. Yildiz Vreken from the Helmholtz Center for Information and Security will discuss interpretability and causality. That will be a little bit more mathematical than what I will discuss today, but in the same spirit. And we then will have some applications. Rampi Ramprasad from Georgia Tech, who is, I think, the key person in polymer research in connection with machine learning, will give us an idea in what is doable in polymer research and real materials. Christoph Koch, who is a top expert in electron microscopy here at the Humboldt University, will discuss AI in experiments, and Lukas Foppa, I mentioned him already, will discuss the application to catalysis. Let me emphasize something which is surprisingly often forgotten. A proper application of artificial intelligence involves at least these 4 issues. Data collection, and second, data management. Getting data, getting good data. And good data means high quality, well documented, well characterized, but also relevant for the topic of interest. You may think that these first 2 points are obvious and good scientific practice. However, you will see that there are still important and not yet solved challenges, in particular in experimental sciences. Obviously, only if number 1 and 2 have been solved, we can go on for doing data analysis or using artificial intelligence tools, And we may go on in looking at the interpretation of results. As I said before, the last point may be debated, but I will say something in a moment. Again, all of this will be addressed in the lectures, which I mentioned, and in the exercises. Indeed, the lectures will be complemented by hands-on exercises, where you will learn how to use the methods that are covered in the lectures. And the exercises are given here. They are a little bit longer than usual, and that's why we take them only or plan them for every second week. They may take something like 3, maybe even 4 hours, and they will be given by people who are listed on this transparency, bringing you really to the point that you can use the methods which are described in the lectures. So let me just mention some literature which I would recommend parallel to the lectures which you will hear. I recommend the following, but in particular I like to say that we will address, in fact, not just standard methods which have been developed in different areas, but we want to focus on material science. So we'll address rather new methods as well, that have been methods that have been developed or advanced for material science in recent years. At these lectures, when methods are covered, additional and more specialized literature will be provided. But here are 4 textbooks which I at least like. The first one, on the left, the elements of statistical learning. I think I said that already. Statistical learning is, in my view at least, essentially the same thing as machine learning. It appreciates that the analysis is done by statistical methods, as you will see during the course. The classical on the left side is by Hastie, Tibshirani and Friedman. Covers really a lot of material. It is from 2008, so 12 years old. The second one is a little bit newer, from 2013. In fact, that is Introduction to Statistical Learning by James, Witten, and again Hastie and Tibshirani. I understand that James and Witten were graduate students of the last 2 authors, and they have done a book which has a lot of things in common with the first one, but it has less mathematics. Sometimes I feel more words, but it's in fact very nice to read. And I recommend that. It also has examples of the machine learning language R, and there is a lot of exercises in this book as well. Another classical book is the third one, which is the oldest in this list. This is from 2000, from Vladimir Wapnik. I think also highly recommendable. And last but not least, Statistical Learning from a Regression Perspective by Richard Berg, which I think is probably the newest one from more or less this year. I think good, and many people may like it. For my taste, it has a little bit too many words for the message, but it's a matter of taste. All these books can be downloaded for free as PDF file. This is at least what I have done. If you have problems with this, please let us know. Of course, Springer would be also more than happy if you also buy a hard copy. So let me start with a little bit of history of material science, and I do this with a question, namely, where and how material science will or has been and is developing. I do this with going through so-called research paradigms. Now let me do a clarification. A paradigm is not just the introduction of a new method or a new concept. It is a new way of thinking. One may even say a novel, not just new way of thinking. Sometimes it is argued in the history of sciences that with a new paradigm, the previously established understanding is no longer valid. This is not true here. A new paradigm in basic research in material science means a new, important and complementary way of thinking and describing nature. And this is the way, and in this way it will open completely new prospects. Some science advancements typically go together with the availability of new methods. Indeed, this is behind the different steps or the different paradigms listed or shown on this view graph. Material science started about 5,000 or 4,000 years before the Common Era, when the Stone Age advanced to the Copper and then Bronze Age. This was when mankind was able to control fire. And this was the basis of what is today called metallurgy. This is the advent of experimental material science. It went together with being able to control fire. Now, what fire was back then is now, for example, a free electron laser. This is why I use these symbols at the top of the first paradigm. The first paradigm, which we call empirical science and experiments. Then it took quite some time, until 1600, that the next paradigm started. Toward the end of the 16th century, scientists began to describe physical relationships through equations. Well-known names from the early days are Tycho Brahe, Galileo Galilei, Johannes Kepler, Isaac Newton and Gottfried Wilhelm Leibniz. The latter two, Newton and Leibniz, also developed the concept of the mathematical differential and derivatives. Thus, analytical equations became the central instrument of theoretical material science. This way of thinking, describing nature in terms of analytical equation, the second paradigm, is symbolized here by the Schrödinger equation. Needless to say, the first paradigm, the empirical and experimental sciences, did not become obsolete by theoretical physics. The new paradigm just represents an important complementary methodology. Since the 1950s, electronic structure theory was advanced for materials by John Slater. The Monte Carlo method was introduced by Metropolis et al. Alder and Wainwright and Raman introduced molecular dynamics. These are the key methods of statistical mechanics. Hohenberg and Kohn and Kohn and Shem laid the foundation of density function theory in the mid-1960s, and all these developments enabled computer-based studies and analysis of thermodynamics and statistical mechanics on the one hand, and quantum mechanical properties of solids and liquids on the other hand. These methods define the beginning of computational material science, what is nowadays considered the third paradigm. Herewith, computer experiments, a term created during these periods, that is, simulations whose results are often treated and analyzed analogously to those of experimental studies. Initially developed independently, the fields of electronic structure theory and statistical mechanics and thermodynamics are now growing together. Likewise, I should say, in parallel to DFT, many body techniques based on green functions were developed, which are now synergistically interleaved with DFT to form the forefront of electronic structure theory, including electronic excitations. Today, big data and artificial intelligence revolutionized many areas of our life, and material science is no exception. This is the fourth paradigm, and Jim Gray was probably the first person who discussed that in depth and called it the fourth paradigm, arguing explicitly that big data reveal correlations and dependencies that cannot be seen when studying small data sets. This vision was first described on January 11, 2007 by Jim Gray, a scientist from Microsoft Research at a Microsoft workshop. And the content of this workshop and of his talk can be read in this book, which was later published by some of his colleagues. This was the last big thing Jim Gray had done, because 2 weeks later, after January 11, 2007, he disappeared with his sailing boat at the Pacific Ocean, and 5 years later, which is a standard timing, he was declared dead. The history and the names which I mentioned and the dates can be found in a recent publication which is called Big Data Driven Material Science and Fair Data Infrastructure, published in the Handbook of Material Science last year, just if you're interested in dates and history. Let us generalize the big data concept by noting the complexity of material science and other sciences. What are the big challenges in general? They are summarized by 4 words: volume, the amount of data; variety, the heterogeneity and the form and the meaning of the data. That means, for example, if you do a theory, it somewhat means that people in chemistry have different names for the same thing than the physicists have, and they have different units, and of course, to some extent, you may say a different language. If you look at computations, there are 40 different computer codes, and they all somewhat have a different type of nomenclature. In experiments, I think it's even probably worse. If you want to compare and use together data from electron microscopy and photo emission and other methods, you really have to be very careful in understanding what people have done. Fighting or dealing with the variety, with the heterogeneity, is a big deal, and we have to do this if we want to create good data repositories. Velocity is another issue, the velocity at which data may change or new data arrive. So far that has not been a big problem in material science, but things are changing. If you just look how data are measured, how fast, be it really on femtosecond laser spectroscopy, but also in electron microscopy, we are coming really to a point that this is also an issue. Veracity, the uncertainty of the data quality, is a big issue. That means we have to identify the approximations or the conditions under which an experiment has been performed. And of course, only if this is done carefully, we can do the big data analytics by artificial intelligence. These terms are called the 4V, plus the goal of this lecture, the analytics. If we have big data, then we can, in the sense of Jim Gray, look for structure and for patterns in the data. And that gives us correlations. It tells us what really is correlated, and maybe we will be able to put things together in terms of a map, which I will describe, in fact, in a moment in more depth. But of course, building maps, finding correlations requires good data. Data are created since many years, often, not always, but more and more, by high throughput screening. In computational and material science, the problem somewhat is that people are measuring a lot of things, but they have a very focused research agenda or research project. And a lot of materials they study do not really fit, do not agree with what they really want. And so people are looking at many materials in this high throughput philosophy, but most data do not really fit to what they want to really study. Now, this is not a new idea. It's sometimes called the Edison approach. When Edison looked at finding a good filament for light bulbs, it was also in catalysis when people more than 100 years ago, that was in fact Arlene Mittasch and in Bosch and Harvard, looked at the best catalyst to create ammonia out of the nitrogen from the air and hydrogen from water. He looked at 20,000, roughly, maybe more, with different materials, and only one, in fact, was finally selected as a good catalyst. So you're looking at many, many materials, and at the end there's only one which is really relevant. What is done, and that is what this figure in fact shows, is from all the materials which are studied, if they do not really fulfill these, say, 5 properties like stability, like good performance and whatever, they are somewhat discarded and they are put into a waste basket. In the past we looked at 20,000 maybe in the Mittasch case. Nowadays people are looking at maybe 100,000 or even more different materials, and at the end only 10, maybe a little bit more of these materials turn out to be interesting. Everything else is taken away and typically not even documented or published. We think this is a big mistake, and so we are arguing, since Nomad has been created, that this culture should change and things should be recycled. Because these are, so our request is recycle the waste. And we had this word, enable repurposing. It means the data are, or the materials or the information is discarded because they do not really fit to the very focused research project. But they could be very well, very interesting for a different research project. So if I look at titanium dioxide, because I'm interested in solar cells, and I find some aspects on the surfaces which are not relevant, I will not really look into this anymore. However, someone else who's interested in paints, titanium dioxide is basically the white pigment in toothpaste and white painted walls and so on, would be interested in this. Or it is, titanium dioxide is a very important support material for catalysis. Throwing away and not publishing data because they are not interesting for your own research project is not a good scientific culture. We think recycle the waste and enable repurposing. Allow that people use the data for a different purpose. Of course, that means we will only get big data if we all work better together, sharing advances science, and that also needs what is called a fair and efficient research data infrastructure. This is so important that we will have actually a lecture on this, and here I only summarize very, very briefly a general concept. FAIR stands for findable. Data should be findable. They should be accessible, like an open access publication. They should be interoperable. They should be described in a way that people who are not an expert in this field can still use them. And they should be reusable, or we call that repurposable, but you can also say recyclable. F-A-I-R. Now, we started with this idea even before this publication, which created this acronym FAIR. We started with this in 2014, and when I say we, this is Claudia Draxler and myself here in Berlin. in creating what we call the Nomad Repository. We invited all our colleagues to upload their data. Now, when I say our colleagues, that means we invited the people from computational material science. We started with computations. In recent weeks or months, we in fact are extending that towards experimental work, and you will hear more about this. But it started as computational. But we also said we don't really want the results only. We want the full input and output files. And the reason is to have input and output files is necessary. It enables us to make data interoperable. There are more than 40 computer codes in the community, and they all use different conventions and concepts. Only if we have input and output files, we are able to transform this into a normalized way. Now, this normalization and further use of data has been done 2 years or 1 year after the going public. So since 2014 we went online. 2015 we started with what is called the Nomad Laboratory. And in the Nomad Laboratory we in fact say that we should use the raw data from the repository, but we should parse them, we should convert them, we should normalize them, and this is what is done and stored in the archive, which contains the normalized data, and therefore the archive now has not only things accessible but also interoperable and allowing people to reuse the data for different purposes. So repository and archive are fair. Everyone can access the archive by APIs, or they can be directly accessed by what is called the Nomad Encyclopedia, and again you will hear about that in more detail. Or the data of the archive can be used for artificial intelligence tools, or the toolkit which has been developed and you will use exactly as this. Last but not least, things can be also used for advanced visualization, basically looking at virtual reality. For example, if you want to understand electron-hole pairs, you could say, actually, I'm the electron, and then I have these virtual reality glasses, and I'm looking really where the hole is, and then I walk through the crystal. So these type of little things you can do if you have big data and, of course, develop the appropriate software. We are nowadays often interpreting the acronym FAIR slightly different. Of course, the old one, findable, accessible, interoperable, and reusable, is still actually valid. But we think actually an even stronger wording would be, say, data should be findable and they should be AI ready. They should be prepared in a way that anyone can use them for artificial intelligence analysis. Importance of material science. So what is known and what is missing? It's quite interesting if you see how many materials have been synthesized. And I'm really restricting myself into inorganic compounds. There are 250,000 inorganic compounds that have been synthesized. I will argue in a moment there are many, many more. But even from these 250,000, we know very little. What would you know about elastic constants? Just actually measured for about 200 compounds. Since a couple of years, there is a lot of calculations, in particular by the group in Berkeley, but measured is only 200 of them. Dielectric constant, heat conductance, and so on and so on. The knowledge which we have about materials is very, very little. For almost every property, we are below 1% in coverage. That's obviously a lot. So there's still a lot of things to do. And many more materials are possible. And so there is a lot of opportunity out there in what you can do really with materials. If you think what you can do with these elements from the periodic table, but you arrange them in the different space groups and in a different number of atoms per unit cell, the number of possible materials is practically infinite. And that in fact means that when I said people are nowadays doing high throughput screening, there is no way to cover this huge structural and chemical compound space by high throughput screening. Whatever we do, even if we increase the number of screen materials, we will stay at a very small number compared to infinity. Another problem, which is somewhat special in material science, is that the interesting materials, say the good catalyst for example, the good solar cell and so on, there are very few. We may look at 100,000 of systems, but we finally may find only 1 or 2 which are interesting. So the interesting materials are statistically exceptional. That also requires certain developments and applications in artificial intelligence or machine learning. So the way we are doing this, and you have seen this picture briefly before, that we say, let's try to create maps of material properties using artificial intelligence methods and concepts. If we are able to find the correct properties, X, the features, then in property or descriptors, descriptor 1 and descriptor 2, the X values, the input parameters identifying the material. If we find these appropriate descriptors, one should be able to create maps of materials where in a certain range you find systems with good band gaps for solar cells, you may find good thermal barrier coatings or good superconductors and so on. Now, this is a two-dimensional plot, and then of course it will be much more complicated. It will be not a two-dimensional plot at the end, but that is the idea. As we cannot really do the screening of all materials, we should use what we have and try to do artificial intelligence in creating maps of materials properties and functions. Now, what do these maps really mean? The maps show us correlations, right? As I said before, the artificial intelligence methods give us correlations between input feature X and some output property Y. But what does this correlation really mean? Is there causality behind the correlation? Is there scientific insight? Can we trust the prediction? I said before, we shouldn't ask for too much, but in fact we have to ask for some of the causality. And this has been stressed and very nicely explained by Judea Pearl, an emeritus professor at the University of California in Los Angeles. So what Judea Pearl is saying is that the correlation, if you have a correlation between feature input and Y property output, if there is a correlation, then you say Y is a function of X. Y is a function of X. No, the function does not mean that it is an analytic function. It is, you can also say it's an algorithm. If you give me X, there is an algorithm which brings me to Y. And this function reflects causal inference, always, if it is based on sufficient information. Now, sufficient information means that we need scientific knowledge in creating the X, or we need really big data. Now, typically we don't have big data in material science, and therefore some scientific knowledge is necessary, with the danger that this may in fact imply also some prejudice. The interesting thing now is that causality is somewhat complicated aspect. In fact, there are 4 possibilities, 4 types of causality if we have a function y of x. The first thing is what we usually, I think, know. X brings us to y, means that x is the actuator, or you can also say f listens, y listens to x. But there's a second possibility, that in fact you see a correlation between x and y, but still x and y have nothing to do with each other, except that they listen to a common actuator. So A determines x and A determines y, but there is no direct connection between x and y, but they, as I said, listen to the third actuator. A third possibility when you find a correlation is that y is a function of x, but the causality is just opposite to what the function writing seems to suggest. Y is in fact the reason and x is the result. The correlation is the same. There is no, and number 4, there is no direct connection between x and y, but they have a common effect that listens to both and screams, I occurred. This is the wording of Julia Pearl. It's called the Bergson bias. In simple word, it means that if you have data which are created in a very biased way, you only use a certain material class for studying some properties. It is well possible that the correlation which you find has nothing to do with the science, but only with your selection, your collection of the data. So that is certainly a big danger, that the way we are doing science, that in fact the data which we create, they have the structure because of our bias and not because of the science which is behind this. These are things one has to keep in mind. And let me just give you one little example from very early times. In fact, that is from 1980, when there was a discussion that there was an observation. There was an observation that people who live close to electric high power lines, that these people have a higher degree of leukemia, of blood cancer. There was a big discussion, actually in this case it was actually mostly in the US, very much in the US, that you have to do something. And so if there was a school close to an electric power line that was actually put down and it was placed to another part, if there was a village or actually some people living close to it, either the power lines actually made a bigger turn, or in fact people were put somewhere else. So the relationship was obvious. There was higher cancer rate compared to the average population. Now at the end, scientists looked at that and found that the electric field and the magnetic field at the places where people lived, coming from these power lines, was actually very, very low. It was lower than the fluctuation which you have in the Earth magnetic field. And so there was no understanding, no reason why power lines could in fact cause leukemia. But then it came out that the people who live close to power lines, people who choose to live there, these are people somewhat from the poor part of the society. And now if you look at the leukemia in the poor part of the society, that is unfortunately also higher than the average society. So looking really at a correlation does not mean there is a causality between this. In the case of leukemia, it was just that people living there were poorer. There was no effect, no direct effect of the electricity in the power lines. So this is things one has to keep in mind if one does artificial intelligence analysis of big data because it could be quite misleading, but one of these causalities which we have described in the Judea-Pearl example, in the Judea-Pearl list, may actually apply. But we don't know a priori which one. Learning from big data is really exciting, a little bit you could say even in philosophic terms, but also really in terms of mathematics and basic sciences. There are very many methods, there are very many concepts. It is also very interdisciplinary. So if you just look how things have developed over the past years or even centuries, there is a lot of ideas coming from computer science, from chem informatics, but in recent years a lot really from linguistics. Signal processing, compression of signals played a big role, and you will see some examples later how the ideas from signal processing play a role in artificial intelligence for materials. Social media, robotics, bioinformatics, intelligent systems, and more. These are the areas which have contributed to developing concepts, and there are the methods which we will in fact also address during this lecture. Clustering, knowledge graphs, compressed sensing, neural networks, subgroup discovery, kernel-rich regression, support vector machine, random forest, and again, more. I hope that at the end of the lecture you have an idea about all of these methods, and you will see the strengths but also really the limits of these methods for classes of questions which we are facing in material science. Now, the name of the lecture, we have used the word artificial intelligence, and let me just explain why. It is generally seen that artificial intelligence is the umbrella term of the methods which we are using. Any technique that enables computers to mimic human intelligence using logical if-then rules, or compressed sensing, or decision trees, or machine learning. Any method falls under this umbrella, artificial intelligence. Machine learning, which I think is nowadays more or less the same thing as statistical learning, is a subset of AI, is a subset that includes statistical techniques that enable machines to improve at tasks with more data. And again, a subgroup of machine learning is deep learning, which is a subset of machine learning composed of algorithms that permit software to train itself to perform tasks like speech and image recognition by exposing multi-layered neural networks to vast amount of data. And again, we will see examples during this talk how you can use deep learning for structure recognition and for many other aspects in material science. With this, I feel that the first half of my talk is done. I will continue in a moment with getting more to basic definitions of statistical learning. But before I do this, I think it's a good point to have a small break and to ask or give you the chance to put some questions to me, which I then will try to answer.